Flexible polyurethane, FPU, foam is a widely utilized class of cellular polymers characterized by an open cell morphology, low density, high elasticity, and excellent resilience. These attributes arise from its three-dimensional interconnected pore network, which enables efficient deformation and recovery under mechanical stress. Owing to its versatility, FPU foam is widely used in bedding, furniture, automotive components, acoustic insulation, and emerging technologies such as energy harvesting systems. The material is typically synthesized by reacting polyols with isocyanates in the presence of blowing agents, catalysts, and surfactants, yielding a tunable cellular structure. By adjusting formulation variables and processing conditions, key physical and mechanical properties, such as density, compressive strength, and elasticity, can be precisely controlled to suit specific applications. Polyurethane, PU, chemistry, first developed by Otto Bayer and co-workers in 1947, is based on the formation of urethane linkages through the reaction of hydroxyl-containing compounds, polyols, with isocyanates. Since then, PU materials have become indispensable across industries, including coatings, adhesives, elastomers, sealants, construction materials, and packaging. Flexible PU foams, in particular, constitute a major segment of the global PU market, which is projected to exceed $100 billion by 2030, underscoring their industrial and commercial significance. Materials and formulation of flexible polyurethane foam. The formulation of FPU foam involves several key components, each contributing to the final structure and properties. Polyols serve as the backbone of PU synthesis. These multifunctional compounds contain two or more hydroxyl O groups, which react with isocyanates to form the polymer network. Polyols can be broadly classified into polyether and polyester types. Polyether polyols, commonly synthesized from ethylene oxide, O, and propylene oxide, PO, are widely used in flexible foams due to their hydrolytic stability and flexibility. In contrast, polyester polyols impart superior mechanical strength, thermal stability, and solvent resistance, making them suitable for applications requiring durability and insulation. Increasingly, bio-based polyols derived from renewable resources are being explored to improve sustainability. Isocyanates are highly reactive compounds containing NCO functional groups and play a central role in PU formation. The most commonly used diisocyanates in FPU production are toluene diisocyanate, TDI, and methylene diphenyl diisocyanate, MDI. These compounds determine the reactivity, cross-link density, and overall performance of the resulting foam. Catalysts are essential for controlling reaction kinetics. Two simultaneous reactions govern foam formation: the gelling reaction, polymerization of polyol and isocyanate, forming urethane linkages, and the blowing reaction, reaction of isocyanate with water, producing CO2. Balancing these reactions is critical. Metal-based catalysts, such as stannous octoate, primarily promote the gelling reaction, whereas tertiary amines, such as DABCO, facilitate both gelling and blowing reactions. An improper balance can lead to foam collapse, shrinkage, or the formation of closed cell structures. Blowing agents generate the cellular structure. Water acts as a chemical blowing agent, reacting with isocyanates to form carbon dioxide, thereby expanding the foam. Low boiling point physical blowing agents can also be used, although traditional halocarbons and hydrocarbons raise environmental concerns due to ozone depletion and greenhouse gas effects. Surfactants, typically silicone-based compounds such as polydimethylsiloxane polyether copolymers, play a critical role in stabilizing the foam structure. They reduce surface tension, enhance phase compatibility, regulate bubble formation, and prevent cell collapse during curing. Fundamental reactions in foam formation. FPU foam formation involves several exothermic reactions. The primary reaction is urethane formation, where isocyanate reacts with polyol to produce urethane linkages, forming the polymer backbone. Concurrently, the blowing reaction between isocyanate and water generates CO2 gas and amine intermediates, which further react to form urea linkages. Additional reactions may lead to biuret structures. The nucleation and growth of gas bubbles during these reactions determine the foam's density, cell size distribution, and mechanical properties. Mechanism of cell formation and pore structure. The cellular architecture of FPU foam consists of interconnected pores categorized as open, partially open, or closed. The formation process begins with carbon dioxide generation, which inflates cavities within the polymer matrix. As these cavities expand and interact, thin cell walls rupture, forming interconnected pores. The final pore structure depends on factors such as wall thickness, drainage rate, and the balance between gelling and blowing reactions. Open cell structures dominate when the polymer matrix lacks sufficient strength to retain gas pressure, resulting in interconnected pores that allow air permeability and flexibility. Conversely, closed cell structures form when polymerization occurs rapidly, trapping gas within intact cell walls. The ability to tailor pore morphology is essential for optimizing properties such as compressibility, airflow, and energy absorption. Modification strategies for flexible polyurethane foams. To enhance performance and expand functionality, FPU foams are often modified through surface treatments or filler incorporation. Surface coating techniques, including dip coating, layer-by-layer assembly, and in situ polymerization, are employed to improve thermal stability, chemical resistance, and environmental durability. Functional coatings can impart flame retardancy, antimicrobial properties, and UV resistance. Alternatively, fillers can be incorporated into the foam matrix during synthesis. Inorganic fillers such as silica, alumina, carbon black, and layered silicates enhance mechanical strength, stiffness, and thermal resistance. Organic fillers, including cellulose and wood-based materials, improve sustainability and biodegradability. Nanofillers, owing to their high surface area, significantly improve interfacial interactions and stress transfer, thereby enhancing mechanical performance. However, excessive filler loading may lead to agglomeration and reduced flexibility, necessitating careful optimization. Mechanical performance and durability. The mechanical properties of FPU foam, including tensile strength, compressive resistance, elongation at break, tear strength, and resilience, are critical for its performance in practical applications. Although inherently flexible and lightweight, FPU foams generally exhibit lower mechanical strength compared to rigid polymers. Reinforcement through fillers and cross-linking strategies is therefore essential. Natural fillers offer a dual benefit by improving mechanical properties while addressing environmental concerns related to waste utilization. Their hydroxyl-rich surfaces facilitate hydrogen bonding with the PU matrix, enhancing interfacial adhesion. Nanofillers further enhance mechanical integrity by restricting polymer chain mobility and promoting a more uniform stress distribution. However, long-term durability remains a challenge. FPU foams are susceptible to environmental degradation, including microbial attack in humid conditions, which can compromise elasticity and structural integrity over time. The incorporation of antimicrobial additives and protective coatings is an active area of research aimed at addressing these limitations. Flexible polyurethane foam in energy harvesting. In recent years, FPU foams have attracted attention in energy harvesting technologies, particularly Triboelectric nanogenerators, TENGs. Energy harvesting involves capturing ambient energy from sources such as mechanical motion, thermal gradients, wind, or light and converting it into usable electrical energy. Among these, mechanical energy is especially attractive due to its abundance and reliability. Triboelectric nanogenerators, first introduced by Jung-Lin Wang in 2012, operate based on triboelectrification and electrostatic induction. When two materials with different electron affinities come into contact and then separate, charge transfer occurs, generating an electric potential difference. Periodic contact and separation result in continuous electricity generation. FPU foam is particularly well suited as a triboelectric material due to its lightweight, elasticity, and porous structure. Its three-dimensional architecture increases the effective contact area, thereby enhancing charge generation efficiency. Furthermore, its deformability allows it to respond effectively to low-frequency mechanical stimuli, such as human motion or environmental vibrations. TENG devices typically operate in four modes: vertical contact separation, in plane sliding, freestanding layer, and single electrode modes. Among these, the vertical contact separation mode is most widely used due to its high output voltage. In this configuration, FPU foam can function as a tribo-positive material, interacting with tribo-negative polymers such as polytetrafluoroethylene, PTFE, or polyvinylidene fluoride, PVDF. Advantages and challenges in TENG applications. The use of FPU foam in TENG devices offers several advantages. Its high porosity and compressibility enhance contact efficiency, thereby improving electrical output. Additionally, polymer-based materials are more resistant to corrosion and environmental degradation compared to metals, making them suitable for long-term applications in wearable electronics, self-powered sensors, and portable devices. However, several challenges must be addressed to realize the potential of FPU-based TENGs fully. The electrical output is sensitive to environmental factors such as temperature and humidity, which can affect charge retention and material properties. The relatively large volume-to-mass ratio of FPU foam can lead to bulky device designs, limiting miniaturization. Moreover, pore morphology and foam thickness significantly influence device performance, necessitating precise control during synthesis. Mechanical durability is another concern, particularly under repeated deformation cycles. The incorporation of conductive fillers and nanomaterials has been shown to enhance both mechanical and electrical performance by increasing surface charge density and improving structural stability. Conclusion and future perspectives. Flexible polyurethane foam is a highly adaptable, multifunctional material with widespread industrial relevance and increasing importance in advanced technologies. Its unique combination of a lightweight structure, high elasticity, and tunable porosity enables diverse applications ranging from comfort materials to energy harvesting systems. Ongoing research focuses on improving the mechanical strength, environmental stability, and functional performance of FPU foams through advanced formulation strategies and material modifications. In the context of energy harvesting, particularly in Triboelectric nanogenerators, FPU foam offers significant promise due to its casamata to enhance contact efficiency and energy conversion. Future developments are expected to emphasize sustainable raw materials, improved durability, and multifunctional capabilities, including antimicrobial and conductive properties. Additionally, a deeper understanding of structure property relationships, particularly pore morphology and interfacial interactions, will be critical for optimizing performance. With continued innovation, flexible polyurethane foams are poised to play a pivotal role in next-generation materials for sustainable energy and advanced engineering applications.